Okay, we'll get started again. There's a lot of this is the most blah blah kind of lecture I've ever held. I'm generally not much for doing this kind of thing, but I firmly believe that people have to start thinking differently to really get into this topic. And one thing is to just blah blah about it, on and on. And we could do that for 2 days, and I think nobody would get anywhere. So instead, we're gonna slide into this Excel-based example where we start talking about numbers and really build an integrated model system and really do optimization. So I think it'll be cool, and a relatively simple but realistic problem. First order right for some field out in the world. We could use this little spreadsheet. So anyway, we'll get away from all this dog and pony show stuff here. But I do want to just we've already talked about the traditional models, theoretical, empirical. Are there any questions or comments that anybody has about any of this stuff? Some other issues with respect to models is some you can solve directly, explicitly. Other models that are iterative require an iterative solution. Iterative solutions, there's a guy named Aaron Zick who of course he and many other people who deal with iterative solutions, as soon as anything becomes iterative, it adds a level of complexity that the decision has to be made. How tightly do I want to converge the problem? Okay, so you get tolerances, you get round-off errors, you get precision, you get the whole. And this book on numerical methods, the numerical recipe book, it's called Numerical Recipes, is really a fine text that talks about solutions to a lot of these problems that are needed when you have iterative models. And then you might have nested multi-levels of iteration. That's like in a flash calculation, the equation of state-based flash calculation. Has anyone programmed that kind of calculation directly or not? You know about the Ratchford-Rice calculation if you've taken my course. That's the lower innermost iterative solution. And that problem itself is a mathematically very challenging problem. There's this Ratchford-Rice contest, and again, people like Nicholson and Zick and a few others have been able to solve the challenge of that to a level that you can guarantee essentially any flash calculation with any set of k values and any composition is solved. That's the innermost loop. And then you've got the outer loop, which is an iteration on getting the fugacities and all the components in both phases to be equal. So that's an outer loop, and these types of problems are notorious that if you don't converge the innermost loop tightly, then that brings a residue of problem that carries into the higher level iterative loop, and so there's lots of complexity there. Model parameters, these are basically the numbers that can be changed and will give different results when the model are run. Parameter estimation, this has a lot to do with where I was on that sketch. The less data you have, the less certain is the parameters that you put into the model, the less certain is the forecast of the model, the less good is the model to you for anything. Parameter estimation is one thing, but then once you start getting data, you can actually tune the data to find what parameters best fit the data. And that's a whole field in itself, the model tuning. Model integration, this is we could say direct coupling, I'm not sure exactly what I mean by that. You could ask, why is it there? Let's see, what would be a good example? I'm trying to think this, the IPR and tubing. If you have a model that provides the what you call the available pressure mark, that's the IPR? Yeah. Okay, so you have a model. Let's say it's, I don't know, what's the petroleum experts suite of programs? Okay, so let's say that let's say that I have my own program that calculates the Fetkovich IPR. Okay, so I wrote a little Fortran program, and if we get the rate and the average pressure, then I can give you the bottom hole flowing pressure. That's the available pressure, right, Mike? Yeah. And then we can go to Prosper with the rate and the bottom hole flowing pressure, and it will give me the tubing pressure. Okay, so that's kind of we've got one program calculating the reservoir IPR and the other program calculating the pressure. That's what, Michael, you're going to have to do between some reservoir simulator and some pipe flow simulator. Okay. And to solve this problem, let's see if I can sketch what I'm talking about. So this is the Fetkovich IPR with rate here and pressure here. And then this is the Prosper lift curve. What did Keith call it last night? His buddy, when he started to intercom, V-lift? That was pre any of us, V-lift. And then he said that disappeared because they stopped drilling vertical wells. So they couldn't use V-lift, so that company went to hell. And okay, so this is the deal. So to solve this problem, we did it in Excel with GoalSeek. Okay, and behind the scenes, what GoalSeek was doing was probably some Newton-Raphson calculating numerical derivatives. I'm not sure what it was doing. Okay, but it started with the first iteration. It started with the rate Q1, and it calculated this from the one program. From my program, it calculated this PWF. Is what you called that, right, Mike? Yeah. And you called this P in? No, available. No.
Well, I call it available and required.
Required. REQ. Okay, required. And then in GoalSeek, which I'm not sure what it was doing really, but it's probably calculating the difference between these, which we'll just say PWF minus P required. Okay, and it knows that delta P, which is what we want to drive that to 0. Delta P is a function of rate because both of these are a function of rate. Okay? Did anybody try to check the GoalSeek solution manually by changing the numbers? Did anybody do that manually? Okay. You could have done it manually. You keep trying different rates. You go over here. You go over here. This could be our second guess. And in this case, this, I don't know what would happen here because this doesn't have a rate. We maybe pick this as our second or third. and then we get a negative difference. And then effectively you get delta P versus rate looking like something like this. Okay? And our first value was there, and our second value was there. And so driving this to 0, well, you don't drive it to 0, you drive it to epsilon. Okay? And the epsilon I care about might be 10 to the minus 6, it might be 1, you know. And if I pick 1, that might cause problems elsewhere. Because if this becomes part of a network, and you're only solving this to, let's say, within this boundary here, you know, then that fact that you didn't converge it tightly, that might cause oscillations in some other part of the network that's being solved. So driving this to epsilon, that can be a critical factor. But if my calculation for a given rate takes 10 seconds, and the Prosper calculation per rate takes 10 minutes, okay, then you're going to want to not let this be 10 to the minus 10, right? That's what maybe Aaron Zick would like to see. Because to get it to 10 to the minus 10, you might have to iterate, even with a Newton-Raphson, it might take 11 iterations. 11 iterations times 10 minutes, that's 2 hours of your time. So what you might instead say is that, well, we're going to converge it within that tolerance, which actually gives you then an uncertainty in rate of about like this. So you get your answer within that plus or minus rate there. And the goal-seek, I think I saw some numbers. It was like 10 to the minus 4 or something. It seemed like I saw something like that. So I'm not sure what I would call direct coupling and tight coupling, but tight coupling would be driving this epsilon to a very low value. That's what I would call tight coupling. Okay. Or low tolerance, loose coupling I would consider where you let this grow to one barrel per day or 1 psi type tolerance. You allow some error. You don't converge it completely. You get along 3 iterations, you're there. Can anybody see a problem in not converging this to a tight solution? What problem might?
Maybe there's no solution. Maybe it doesn't cross. Maybe it kind of become low and never have a solution.
Okay, but let's just say that if we had a solution, converging it, where might that be a problem then?
And if the function is very kind of become parallel to the axis before it crosses, the range of Q, and
If this becomes very flat, something like that. That's what the Ratchford-Rice function looks like, and that's why sometimes it's hard. Because then if your tolerance is as I've drawn it here to here, then we might get an answer there, and we might get an answer there. That would be within the tolerance of delta P. Now, why might that cause a problem? Well, it's mainly because if this calculation is at the innermost level, and we've got 10 wells, and we're doing the same thing for all the 10 wells, and we're trying to figure out, in a network, how these 10 wells are interacting. Okay? Then the fact that you have for each well a plus minus, let's say on the order of 1 barrel per day, okay, instead of some really tight tolerance. What that would possibly mean is that when you start taking derivatives in the overall problem that you described, which is solving another iterative problem where this comes into play, okay, and I'm just going to try to sketch that here. Let's say that is some variable here in a network problem, and this is our function as our function of the variable as Bjarne was talking about. But this, going into this, is basically the rates for all the wells, 10 wells. Okay? And let's say the variable is something related to total rate, but the total rate's distributed amongst all the wells. So what happens is that this function is going to be, it's not going to be smooth any longer. Because, okay, it should look like this maybe. If everything was tightly converged at a well level, it would be a line like that. But the problem that you're seeing here is related to the fact that, unfortunately, of the 10 well inner loops that we did here, all of them had a positive error. And so you get this big effect here. Right when you were doing this one, they happened to all cancel out, so it was okay. Now this blue curve is not differentiable, so you can't use a Newton method to solve it. Okay, and then what's the next alternative is to use interval halving or some much slower method that takes more iterations. And already it's taking 10 minutes per call per well. Okay? And so you end up, so you introduce into this new function for the network of 10 wells. Each well is now contributing, in a sense, noise to this function because you chose this number here instead of 10 to the minus 10. Okay? So that's a problem. And so if you have loosely coupled models, you basically have to avoid the hope of using derivative-based methods to solve that problem, because you get too much noise. Okay? And non-derivative-based optimization is typically much slower than derivative-based optimization for nonlinear problems. So that's going to be a problem here. But it's very difficult to tightly couple slow-running models. And maybe my implementation of a Fetkovich equation, which requires iteration, maybe I'm a sloppy programmer. So maybe even my calculation of the IPR is jagged, because I'm a bad programmer. Okay. So in general, when we go to models, in the models we have no control over how accurately they're calculating their results. Direct or tightly coupled models is you can almost forget it. And if you forget that, then you can't use derivative-based optimization algorithms. And then you're to the point of using non-derivative-based methods. Model integration, sequential basically means that, for example, in our case of reservoir model A, reservoir model B, and reservoir model C, and then we go into pipe calculations. Okay, and then maybe this goes, we've got a splitter or something, and we have a process 1 and a process 2 going on here, and then maybe some of the products from here go together into a further processing, maybe a gas processing. You've got a process 3, and then this goes off somewhere else, and this goes off. So what we're talking about here is that these various models, these A, B, and C, in a sense, can be run in parallel, right? But you can't do the pipeline calculations until all three are completed. So this would be a sequential. So basically, these models are going to be set up sequentially or in parallel. And orchestrating this is an issue. You'd like to keep your CPUs busy all the time, okay? And how to do that to maximize the use of your available CPU units that are there that you can make use of. So orchestrating the launching of all of these applications to keep these guys busy. Connectivity, we talked a little bit about that. That can be related to just, I think I've got maybe a slide. I don't know. Connectivity, you could have simple file format changes. You could have translations of information from one model to the next. You may have the issue of the possibility of through memory versus through files. Basically transferring information from one model to the next. Nesting, branching, and looping. At this point here, you may have branching criteria. Where to send this could be our routing, basically, our routing problem. Manifold separation into the different here. Looping would be, for example, this is our gas processing, our dew point controller. So the gas here might be going back, being re-injected. But then maybe this becomes another branching, meaning that we have this routing, where to send the gas, A, B, or C. So we've got basically looping data. This is coming back. Information from downstream is coming back to the upstream. So there's lots of computational issues about how to orchestrate all of this going on in an efficient way. So optimization we've already talked about, having a target or goal to either minimize or maximize or simply find feasible solutions. Weight factors and scaling, this wasn't discussed, I don't think, the first 2 days. Yeah.
integration, which part really needs to be tight or loose. Otherwise, like if you start loose coupling since reservoir, then you have a decision variable in the process that has a standard deviation that is really a low resolution on that sensitivity that you're going to do. So we need like to understand like some pre-request. You cannot use loose coupling because the process is asking you to use more tight, or on the other hand, sometimes you use loose coupling because you know that it can give you better performance.
Yeah.
Then how can we understand that you can play with that or
Well,
being a consequence of who developed? Should we
it's part of the when you couple two models together, it's part of the experimentation you have to do with the coupling. You have to decide if there's, in a sense, a feed kind of a if there's an iteration to convergence in the coupling, then you have to study how tightly you have to converge it, not just for the accuracy of the answer, but the impact of that accuracy of the answer downstream in the overall system. Yeah, and that's really what we were talking about on this other slide, on this one here, is that if the objective function, your f that you're creating in an integrated modeling environment, is not smooth as a function of all of the variables you're changing, it probably won't be, almost very seldom. If it's not smooth because of this looser coupling, or because one model doesn't converge itself very, very accurately. Okay? There may just be one model out there that has sloppy tolerances. You have no control over it. Well, there's no reason to couple to that model tightly. Okay? You're just guaranteeing that you get the noise that it gives you, that you keep that noise intact instead of introducing new noise. So I think inevitably what we're going to see in integrated models, systems like we're looking at, are objective functions that are not smooth as a function of some or all of the variables. And that consequently moves us, that would immediately move us away from derivative-based optimization. Okay? I think that's a very important conclusion.
And how about the error propagation also that we would connect both this way of coupling to error propagation, because when you start the calculation long in reservoir, you are propagating your error, and in the end you're not going to have accuracy for your optimization.
Right. Well, that's kind of what this red, the difference between the red and the blue here. That's kind of an error. Now, this is an okay kind of error because the error is not growing. Okay? But if the magnitude of this is 1,000 cubic meters per day, then you might start saying, well, that error of 1,000 plus, it's plus minus 1,000 cubic meters per day. Maybe that is important in itself. So the magnitude of it. The problems that you really don't like to see would be problems where the error is growing. Okay? Then, or you get these large oscillations, and you. So maintaining enough coupling that in a sense, the error propagation doesn't grow beyond what you can accept. and preferably doesn't grow, but is kind of balanced. That it grows and then it goes down, and it grows. That it's kind of, it's there, you accept it, but it's within a certain tolerance. I think that's this issue of how tight you couple various models, how tight you drive the convergence iteratively. Is if you abandon derivative-based methods, okay, you just say you can't use them, that's fine. Then all you're really concerned with is the magnitude of the error being propagated in the system. If the net present value is uncertain by 20% because of error propagation, then obviously that you're in trouble. You have to go in and start tightening the coupling or the convergence criteria. This F that Bjarne was this objective here. If this is a instead of it being the objective being to maximize net present value, okay, instead of it being that, let's say that the function is, in a sense, the sum of errors between measured data and model data. We're tuning a model, okay? If it's the sum of a bunch of errors here, for example, like in history matching, so then what you're going to want to be doing is to try to minimize this function by changing various parameters in the model or models. These errors, which I can call, it's usually called residuals or something. It can be all sorts of types of data, rates, pressures, gas-oil ratios, whatever you want to, okay. We could say this could just be deviations, okay, just normal deviation, something like that. Deviation between a particular data that's calculated from a model minus the observed data over the observed data. Something like that would be a deviation. Well, typically this kind of residual would be squared, and then it would be weighted. Okay? The weighting is done because, well, statistically, if you have an infinite number of data measurements, okay, and you have data uncertainty, simply that the measurement error, there's uncertainty in the measurement of the observed data, okay, there's a plus minus there, a distribution of uncertainty there. That will lead to, for some data it's a bigger uncertainty, and for other data it's a smaller uncertainty. That would lead to a formal definition of how you define the weighting factor. It has to do with the standard deviation of a particular type of data. But that you never have. You basically, that's not what's used. Instead, what we have the weighting factor does is it says these data are either more important to me or they're more accurately measured or both. And I really want to emphasize getting these data fit right. These other data I don't particularly care whether they're fit accurately or not. They might be very accurately measured, but I don't really care about the data. Okay? So the weighting factors kind of emphasize, if you will, that's the word used, they emphasize different types of data. And if my emphasis is different than your emphasis, we no longer have one function that we're minimizing. We have a Curtis function, and we have an Ahmad function. Okay? His emphasis is different than my emphasis. And all of a sudden we get subjective, objective functions, right? And if we've got 30 people here, we've got 30 objective functions. You can use the same algorithm to minimize it, same set of variables, the same everything, but we all define different weighting factors for our data, and we'll end up with 30 optimal sets of our parameters for the model. Okay? 30. We use the same definition of residual. We use the same 3,000 data points. But we all go in with our own bias, our individual bias, what I think is important, what you think is important. Okay? You're lazy, you just leave them all go to 1. We might have 6 of those. Okay? No weighting factors. And we end up with all these different, and every one of them is different. And they're all going to have a different, if you will, minimum. If you just have one variable, x, 1, then this is the Curtis, this is the Ahmad, and this is the Mike. Okay? And my optimal x1 is different than Ahmad's is different than Mike. Okay? Just because the weighting factors are selected differently. Everything else is the same. Same algorithm for solving it, same variable, same data set, everything. Okay? So the weighting factors is often something that's not given much attention to, but it should be. Scaling, when it comes to optimization, basically x1, if it's often given like that. Okay? And x might be something like that for some particular x1. I don't know what it would be. You know, CO2 concentration. I don't know, some variable. And x2 might range from 10 to the 4th to 10 to the 6th. Could be pressure in Pascal or something. Okay? If you go to Solver with this kind of problem, I don't care how simple the function is, if it's nonlinear, and you try to solve this, it's probably not going to find the optimal x1 and x2. Unless you turn on the little option called scaling. I think that's what it's called. Okay? And what the scaling does, it's not default. What the scaling does is that it transforms into a new variable, something like this, x1 minus x min over x max minus x min, something like that, some kind of scaling. And it solves for x star 1 and x star 2. And 50% of the time I use the solver, I'll have to go and ask it to use the scaling. Why it's not default, I'm not sure. Parameters, constraints, we've talked about that. Global and local, that's what Bjarne called convex. I never knew it was called that. Convex is that there's only one solution. Is that right, Alex? It's there. So if you find it, you're done. If it's non-convex, then you've got a function that looks like this. Okay. Okay. If you start from the left, you'll reach this probably. If you start from the right, you'll reach this. I just call it, it's a local, this is the global minimum and this is a local minimum. Practically, how do you know if it's a global minimum? You don't, ever, unless it's a truly linear problem, I guess. If it's a nonlinear problem, you'll never know, I don't think, because you have to try every combination of every variable in space before you know for sure, 100%. You just never know. Practically, what I like to do to see whether it's likely or not the global minimum is that you start all your variables, you start with 1, 5, 10 sets of initial variables, and if each time you start with a new set of your variables and you get to the same solution, if you do it several times from different starting points and you still get to the same solution, that's a pretty good indication that it's a global solution. I don't know if there's any other good ways to do it, but that's the only way I know. Yeah. Huh? Genetic algorithms, and you basically are looking over a larger piece of the real estate, right, for that minimum, and so okay. Derivative-based and non-derivative-based, that also was not really discussed by Bjarne, and what I think is guaranteed in the majority of integrated model optimization is that we will not have a smooth function, a smooth objective function. Smooth enough to take derivatives. And you can then more or less abandon the idea of using derivative-based methods. So that's probably seldom can be used. Some problems, if you have very, very good models that converge tightly, sensor is an example of that, phase comp is an example of that. Okay, where the people writing the models are particularly paying attention to converging their solutions tightly. Okay, no sloppiness allowed. If you only have models like that, there's a chance that you can use derivative-based optimization, at least around those models. You get one sloppy model in the integrated system, forget it. One sloppy model is all it takes. Then you have to go to these non-derivative methods. Okay. I don't think I need to we've already talked about this, really what we're in optimization. I think I may come back to this later, but I think what I want to do now is I think I want to move towards kind of a hands-on example of what we've been blah-blahing about now. Okay? We get a feel for this. So the environment that we're going to build integrated model and do optimization with, we're going to use Excel as our platform for integration. We're going to use Excel equations will be our models. Okay? In Excel, each cell can have an equation, right? And that will become, we'll have many of these little models, and they'll be integrated in various ways, and then we'll try to do some optimization. So actually the last couple of days you've been doing integrated optimization, but in a little different way. So what we're going to do now is okay. So this is this is going to be the problem. We're going to have a petroleum production system where we go from the reservoir. We're going to include some production characteristics, meaning flow and pipe through the tubing. We're going to have reservoir flow, basically the IPR and the lift curves. That's what we call the reservoir production proxy. There's a material balance there, which says that as we take out production, in this case it's going to be a gas reservoir. As we take out gas, the average pressure falls. So the reservoir has a tank material balance, a gas reservoir equation, and a pipe flow through tubing built into that one model. And then we're going to have another model, which is the processing. And we're going to take the gas stream that's generated by the reservoir production model, and we're going to allow that to be processed into 2 or 3 products. Certainly gas, one. And then we're going to allow processing of the gas to get a gas liquids. Okay? And how much gas liquids we obtain will depend on the temperature in this processing unit. Okay? So if we have a very low temperature, then we get a lot of the very efficient extraction of the gas into liquid. And if we have a higher temperature, then we don't get any liquids from the gas. Okay? So it's a very simple process model. And then we take the products of what's been created, the gas, sales gas, and the gas liquids, and we have pricing, discounting to a net present value. Okay? So that's conceptually, and once this all works together, we'll integrate it so that you can change any parameter in any of these models and you'll immediately see the effect on the net present value. So you can just go in and change numbers and go over and look at the net present value and see what's done. That's the idea. So what we're going to have to do is, so it's not completely a black box. Let's see here. I thought I had already done this. I think I just didn't save it, maybe. This is our model for the reservoir and production proxy model. And the main control variable that we'll look at will be this tubing diameter. And in this spreadsheet, it is all of my spreadsheets, any number that's in red, I've also made the text in red, but any number that's in red, you can change, and everything should work in the spreadsheet. If it's not red, don't screw with it, okay? It's up to you. But if it's red, you can change it. Now, I'm not saying that if you put a negative tubing diameter, it might crash. I don't know, okay? But basically, that's the philosophy here. Red numbers, you can and are allowed to change, and all the other numbers you're not. Now, we're going to have to look at this. So this model is such that you give the following input, and we'll look at the reservoir rate equation. That's basically your KH and skin. Okay. So I'm going to come back to this, but basically it's the permeability, thickness, and skin drives the A. So if you have a bigger KH, you want to double the KH, then you would double A. Okay? I think that's the way it works. Maybe it's 1 over K. I have to be sure of the equation. We'll write these down. And then this B is the tubing constant, which we'll look at in terms of the rate calculation of rate. And this tubing constant is for a specific tubing diameter. Okay, now you can change this one up here to 125, and you should get the actual B that's used in the rate calculation is given over here. And that would be, if you use the same tubing diameter as this, then you get the same tubing constant. If you use a bigger tubing diameter, then you get a smaller B that's being used in the calculation of rate. So anyway, this tubing diameter will affect the tubing constant over here. We've got the initial gas in place. We're making the assumption that we sell to the purchaser a fixed amount of the initial gas in place per year. That's a typical way to set up a gas contract. Here it's 4% per year. Maybe it's and then for how long we're going to sell the gas in the contract. This is the initial pressure of the reservoir, and this is the minimum flowing pressure. Now, the rate equation is shown here. Okay, so that so the rate equation combines a reservoir plus tubing. Okay, we have a gas reservoir, a gas field, if you will, and the rate equation is B Q squared for a well plus A QW minus P average reservoir pressure squared minus P tubing pressure squared equal to 0. So this is our rate equation for a well. This is basically representing the tubing pressure losses. This is representing our reservoir pressure losses. And this is, of course, the total pressure loss. A is proportional with basically this KH and skin are the main parameters. They're looks like this. The higher the KH, the less the reservoir pressure drop, right? That's a first order effect. Okay? The higher the KH, proportionally the delta pressure squared, if you will, becomes less. The B is proportional with 1 over the tubing diameter to about the, what was it, 2.7, I think?
2.65.
We can check it here. I've got the 2.6. Okay. So there's a strong first order effect of tubing diameter on the tubing pressure loss. Okay? First order effect, KH. First order effect, skin. Now, how is this? How is the rate equation being used here? Okay. The field gas contract says that we produce cumulative gas production at the end of plateau is what? Well, it's the gas in place times the number of years of plateau times what? This fraction, 0.04 in the case of the example here. That's the recovery factor per year. Okay? So that's the total gas produced. And then we use a very simple material balance that says that the average pressure in the reservoir, but seen at the surface, don't worry about that. It's just the average reservoir pressure in the reservoir. But if we had an observation well sitting out there in the field, just shut in the middle of the field, and we looked at the pressure at the surface at any time, this is the pressure we would see. That is equal to the initial pressure in that well times 1 minus GP over G. Okay? After you've produced half the gas out, you have half the pressure. This is a first order correct model for coming up with the average pressure. The average pressure obviously is a first order variable in this equation. Now, what happens at the end of the plateau? Okay. Well, let's look at what Mike talked about yesterday, is that that's time to plateau. This is the gas field rate. And we're going to say that's equal to the well field rate times the number of wells. Okay? So, essentially, let's say if n number of wells happen to be 10, then this would be, that would be the well rate, be constant. Okay? If we look at the choke opening to be following what we talked about the last couple of days, from 0 to 1, for each well, pick any well, they're all the same. All of our wells are the same. Then day 1, we can have the choke opening to deliver this rate of 5% opening. Okay? But then what's going to happen is that this is going to do something like this. And then when we reach plateau, the choke's going to be fully open. And it'll stay that way. Now, what happens to the rate then? The rate's going to then start declining. That, like that. Okay? So, let's look at one other thing, and that is the flowing surface pressure as a function of time. Mike called it P wellhead, flowing tubing head pressure. Okay. As a background, I'm going to put PC in here. This is PCI, and that's going to keep going down and down. That's our average reservoir pressure. And the PT there is going to look something like this. It's also going to go down until it gets about right there. And then when it reaches this point, it's now reached the minimum we allow it to go to, and it's going to remain constant. Like that. Separator pressure. Okay? For example. This, as Mike was talking about yesterday, is a key first order variable. You put that in the spreadsheet, minimum flowing pressure. That's this one right here, 75 bar. So what we know is that at the end of 12 years, we've produced 48% of the gas in place. That's 0.04 times 12. We know the average pressure at that point. That's 130 bar. We know the flowing tubing pressure at that point, PT. So basically this at the end of the plateau, this will be PCI times 1 minus recovery factor at 12 years, 0.48. That will be our PT minimum. Can't open the choke anymore. It's equal to the separator pressure, whatever. And then we can calculate the gas rate at the end of the plateau, right? So we can calculate the gas rate of a well at the end of plateau. But what is the field rate at the end of plateau? That's 0.04 G, right, per 365 days. Right? This much gas per year, so that's the rate of the field. So the number of wells you can calculate. Okay. That's the rate at the end of the plateau. That's only a function of basically the recovery factor at the end of plateau. You change the recovery factor at the end of plateau, you've changed the average pressure. It's also, of course, a function of PT minimum. Okay. So if you change recovery factor, PT minimum, how much you take out per year, gas in place, on and on and on. These are all these first order effects that will affect how many wells it takes to make sure you can deliver that gas rate at the end of 12 years. And that's the main result of this sheet. You change any of these numbers. This is the B correcting for the tubing diameter. This is the well rate at the end of plateau. That's the field rate. That's the average pressure at the end of plateau. That's the total recovery factor at the end of plateau. and that's the pressure drop at the end of the plateau. Based on that, we can calculate the number of wells required, which is the field rate divided by the well rate. If we change the diameter to a straw, we need 1,000 wells. That is the size of a straw, 10 millimeters, right? That is a Coca-Cola. That is a McDonald's field development plan. Okay? And if we put 1 meter, or 1,000 millimeters is 1 meter, we need 14 wells. That's a monster piece of tubing, right? We don't have 1 meter tubing wells. The biggest tubing in any well in the world is 13 inch. It's about this size, and that's about 0.4, so about 400. That's the biggest you can get. Well, you see it didn't change that number, 13.6. It still needed 14 wells. This is an integrated reservoir production model. If you change any of these numbers over here, gas in place, if you want to sell more gas faster, we go to 6%, it doesn't work. You can't go for 12 years. You can't go for 12 years. You can sell 5%, so you've got a 60% recovery at the end of 12 years. It takes 44 wells instead of 14. The number of wells is a primary, if not the primary, cost item for a gas field development, because the number of wells means how many templates or how many platforms, etc., how many wells have to be drilled. So it's a key cost item. All of the main variables that affect the number of wells are basically captured in this spreadsheet. Tubing size, KH and skin through the constant A. Gas in place, how much you sell to the Germans each year, how long they want to keep buying it, the initial pressure, and the minimum tubing pressure. These are, for gas development, the only main variables that you have, basically, in most cases, if it's a tank. Okay? First order effect model, very fast, computationally efficient, and you end up with an estimate of the key economic result is number of wells required to deliver that plateau. Is the model clear? Now, how many do reservoir simulation or have done reservoir simulation here? Okay. How many reservoir simulators can accept the equivalent of these data? The tubing diameter is a tubing table, right? No problem. A is KH and skin. No problem. B, again, that's tubing diameter. Gas in place, that's an input to the model, right? How much you take out of the field. You can have a platform and you say this much per year. No problem. Plateau period. Do you put in a plateau period? Is there a plateau period keyword in Excel, Eclipse? I don't think so. Okay? So, but you can put in minimum tubing pressure. That's an input. Initial pressure is an input. Plateau period you don't put in to the model. So how does Eclipse 100 tell you how many wells you need to produce for 12 years? How do you do that with Eclipse? Or sensor or anything? You don't. You have to run the model time and time again, right? Until what happens? You keep putting in a well, you put in another well, you put in another well, and you get a longer plateau. And maybe you make a plot. You estimate the number of wells you think you need, and then you put in that number of wells. And where you put them, I don't know where you put them. You put them uniformly distributed. You put them in the northwest corner, okay? there is no mechanism for it. But effectively, that's what you would do to give the same exercise with a reservoir simulator. Now, what would be nice if you built a reservoir simulator where you could change the number of wells with a single variable and then let it run, and you would see how long it had a plateau. And then you could do an optimization and change the number of wells until you got the 12 years plateau. And that's the only way you could do it, manually or possibly with some kind of an optimizer wrapped around the reservoir simulator. Okay? And here we've got basically one sheet. This is our surrogate for the reservoir simulator. And I can guarantee you that it's going to give you essentially the same answer if you take the time to put in the tubing tables and da-da-da-da-da. Okay? If the permeability is above about 1 millidarcy or even probably 0.1 millidarcy, this will give you the same result as your 100,000 grid cell gas reservoir model. Okay? So you may not believe that, but you can confirm that to yourself. I mean, that's up to you to do. I've done it before. Okay? But what I'm saying is that we have a surrogate proxy model for the reservoir in production that I can go good for. I'll bet you a month's salary. Okay? That's not very much at the university, but I'll bet you that a month's salary that your 100,000 grid cell problem will give you the same answer if you put in the same data. Okay? I feel confidence in that. But here, that's a lot easier than creating a whole new, going to the Prosper, choosing your correlations, learning how to use Prosper, debugging the results from Prosper. I mean, I've gone down to the cellar to try to use Prosper. 3 hours later, I came up. I wasn't sure where I was. You know, I didn't know which keywords and which Orkachevsky, and I choose that one because I can't spell it. I figure it must be the best. So, but again, if you've got all these key variables and you've got a key result, that's this model. Okay. Any questions about? And it combines what Mike was talking about. It combines in this equation here. This actually solves direct. This is a direct solution to the IPR plus vertical lift calculation. This is a direct solution to that. It's a single model. Okay, now what might we want to try to optimize here? Just the reservoir and production group. Huh? Tubing size? Okay. All right. I've done my work. You guys got 10 minutes to tell me what to do. We're going to optimize tubing size here. So, suggestions how to go about doing that. I mean, I can change this. I don't know what I did here. I just wrote. Oops. Okay. Now that. Okay. Okay. What do we want to do? We want to have what's our target? Minimizing the number of wells. Okay. So let's set that up with solver. Okay. So the target cell is this guy here, and we want to minimize, right? Okay. And we're going to change that. Okay. And anything else to do? What kind of constraints? Huh? Tubing diameter less than 400. Okay. Why 400? Okay. So add that this puppy is less than or equal to 400. Okay? Any other constraints? Okay. That was the McDonald's straw. Okay. So we go to that being greater than or equal to 10. Oh. That? Okay. Any other constraints? Before, yeah. Well, do you want to add minimum tubing pressure? Okay, but that's not being changed, tubing pressure minimum right now. If you start using that as a variable, then you might set constraints.
Right now the answer is under 400.
Because?
Because that would be
Yeah. If that's your supposition. Of course, we can test that, but I think you're right. And we do that by experimentation. I'm going to just close this now. We go 10. That's a lot of wells. And we go 20, which is a milkshake straw, and 30, and 50. See, what's Oklahoma tubing? That's 2 inches. That's about Oklahoma tubing, normal tubing. 330 wells.
But you don't put any limit on the number of wells.
We just like as few as possible, I guess. Or we could say that we have to drill 50 wells. This country says you have to drill 50 wells no matter what.
If you don't drill it, you lose the acreage, so you might have a certain minimum of wells.
Okay, that's another problem. But we can come back and try that one. But Mike's saying that if you had to drill 50 wells no matter what, okay, then you could try to optimize what size tubing do I need for it to take 50 wells, right? It's a little more interesting problem than what we're doing here. Okay, because this problem is like you were saying, that if I just keep going to 400, it'll say I only need 44 wells. Okay. Did I change something else down here? I think I changed this to change that back to 0.04. 14 wells. Okay. So the smaller the tubing, the more wells. Not very much more well. Okay. So if we run this optimization, like you said, then it should find 400. That's true. But now we go and Mike's got a little more interesting problem, and we say that we want 50 wells. What's the tubing size I need with 50 wells? Let's say 20 wells. Okay. Okay, so now we have to introduce a new
Huh?
huh?
You can just change figure into the solver.
Okay. Oh, yeah, because you can have an equal one. Okay. All right, so we go there, yeah, and value of 20. Oops, that's not what I wanted to do here. And, solver, value of 20. By changing tubing diameter. Okay. Yeah, I think that's right. Yeah. Okay. There we go. See, it didn't get the same answer coming from one direction to the other direction. Okay. If we started with 200, I think, it didn't find it. I found it there, but it was 400. Okay. Now, why is it not finding it? Why do you think? Hmm? I don't think. If we do a little experimentation around 400 wells, I'm just going to say 390, 380, just looking at it around here, and number of wells, okay? Let's just do some experimentation. But I'm going to need more digits here, I think, to make my point. Now, when it tries to solve this, it starts at 400, and it's going to do a derivative calculation to use Newton. And it'll change it from 400 to maybe 10 to the minus fourth less or something, so it might be 399.9. So let's just set up our and then that was, I'll just copy this down to here. I'll paste special value. I'll give it, okay, it's got lots of digits there, so I don't have to have digits up here. And now, I'll put that there. I want to have these the same number of digits. Something like that. So I'll change this to 3. Actually, I'll change that to be equal to this. Okay. Now I'm going to change this to 399.99. Okay. And you see it changes only the last digit. So my suspicion is that the derivative it's getting is not reliable because it's very flat. There's very little change in the number of wells around here. So this function is very, very flat. Basically it's an asymptotic. There's an asymptote here when it goes to infinity, which might be 13.642. Okay, and we're right there, and then it's doing a derivative, and it's still right there. You know, I think it's probably the precision of the derivative. Now, in the solver, that's something you can control here in the options, I think. Precision, convergence, tolerance. I'm not sure what these mean. What do you think? Precision?
Tolerance maybe for convergence criteria. Change the precision.
Precision, I think, maybe is what I think precision may be this delta in the calculation of the derivative. So let's get rid of 1, 0, or 2 here. Give a little bigger change in okay. And then what we can do is we can also look at the steps like that. Let me just, yeah, and then we'll be watching this one, which is linked up to there. Okay. Solver. Okay. Solver pause, and it's 13.6414. Okay, that didn't. Okay. So let's try it again. First step, see, we don't. Yeah, you see here it's 399.99. That's what it changed. Did I change that, or is that the one it changed? Okay, let's move it like that. Yeah, see, that's 399.9996. And effectively, it's not getting any change in the number of wells. So the derivative is either infinity or something. I don't know what. Okay, so let's try to go back and change that again. Do you think it's still the point one, as low as that? Okay. So that's not changing. It doesn't seem.
Can you try another method?
We can, I suppose. Here?
I don't know.
I don't either. Put that back to whatever it was. Okay, still doesn't. Okay, you see you got a problem. Okay. This is just inherent in its number of digits. It's but since we wanted an answer, and we were, Bjarne can go and maybe figure this one out, I don't know. But since we wanted an answer, we can start from a straw, and it'll find that. Let me just get rid of all these options here. Go back to this. And it's 135, which is what size in inches? Inches divided by 25.4. Now, so 6-inch tubing. Is that right? If we have to drill 40 wells, oh, I got rid of the equation here. That's not good. Have to put it back in. What was the equation? Field rate divided by well rate. So if we're at 40 wells, we have to set that to 40. And it's 3.5-inch pipe tubing. Okay, so that's an example of how you might. The other example of just finding what tubing gives the fewest number of wells. Well, that's 400. But on the other hand, if the task was to find the best tubing, that was the original question. What is the best original tube? What is the best? What is the optimal tubing? What do we mean by that? The smallest, right? Are we sure it's the smallest or the largest, the fewest number of wells? But if you go to 400 millimeter tubing diameter, then the well, I mean the casing, I mean the cost of the well is going to be 10 times the cost of a normal well with 7-inch tubing. Probably 10 times, you think? 5 times? To put in something that's never been done. So you're going to have new equipment made, you're going to have, okay? So there's going to be this very strong cost escalation per well if you go above a normal tubing size. So the reservoir and production engineers have no idea what that cost function looks like. So it's impossible for us to really optimize on the tubing size. Okay? Because the wells that we can say that cost 100 million crowns per well, or 50 million, or $10 million a well. That we understand. But we have no idea of the escalation of that base cost as the tubing exceeds normal sizes. That's a cost function we have to work out. Okay? Right now we can't do an optimization, other than the case where we know the number of wells and we want to know what size tube. That we can do here. Okay? Is there any other kind of optimization we could just have them do?
Well, the question is that you put, the way you do it here is that you put infinite amount of wells. Then the problem is probably when you increase the number of wells, at a certain point they start to steal oil from each other. Then probably the B or A should be changed. It's not a constant.
Okay, Mike's point is this, that A is equal to KH over log RERW plus skin. Okay? And RE is equal to the total field area divided by pi square root. Okay? And then number of wells. Let's see, number of wells here. Okay. Okay. So let's say that's equal to some constant C, 1 over square root of number of wells, right? So if we say that for normal number of wells of 10, I'm just going to say RE is equal to 3,000. Just instead of picking an area, that's a normal RE. Okay, so then we basically get, or let's say that log, and then log RERW would be log RE star RW, 1 over square root of NW, right? We say this term is 8 instead of this. Then this term would be 8 divided by square root of number of wells plus skin over KH. Okay? So that we could introduce into the...
Once RE becomes close to W.
Right. Okay. So this is going to bring in a sense, I don't know whether there'll be it'll create some kind of optimal, but we can add this. This is a more refined. This is only going to be important if NW becomes large. And in fact, this is not even quite right because it's the logarithm of this. So that's equal to log RE star RW plus log of, actually that would be minus log square root of N, which that's equal to 8 minus a half log NW, right? Okay, that's actually, this is going to be the equation. So to do that, we have to add base log RERW for 10 wells. Okay, so that would then make this, we put that over 10, right? Because if that's 10, then this term goes to 0. Okay? So we say that's 8. That's 8. And then this A term is that times 8 times this divided by let's see, 8 minus 0.5 times natural log of number of wells divided by 10. Okay, so it's a circular.
Yeah, so you can use circular in Excel.
We just have to allow it in
When you do it, the option
Tools, options,
in the middle.
here. Okay. So now we're going to try to go back to this original optimizer where we try to minimize the number of wells, right? By changing the tubing diameter subject to these constraints. So now what Mike says is that as this number of wells becomes large, the A constant, the log RERW term up here, that RE becomes smaller and smaller. So the A term will increase, not very fast, but it'll increase. No. So there's no, doesn't look like, you don't reach it by 400, and started at 10. Make sure it's not dependent on the starting point. If we change, just to make sure we did it right, if we change that to 10, you see it does change A here for the 10,000 wells, but the A doesn't change by much at all. You know, factor 50% for between 15 wells and 10,000 wells. So it's obviously not a real first order effect. I mean, because it comes inside this logarithm here. Yeah. Any other ideas on turning this into a local optimization for the reservoir production group? Okay, I'm going to give you one. We'll do lunch at 12:30. This is something you all can do. I want you to find the initial gas in place. This is news discovery, and there's an uncertainty in the initial and gas in place. And if we have a maximum of 30 wells that we can drill based on preliminary economics, 30 wells is the maximum number you can drill. How large does the gas reservoir have to be? Okay? How large? And the maximum tubing size we'll let you use is 7-inch. Okay? So this is the problem. So max 7-inch tubing. That means the inner diameter is 6 inches, which is times 25, 4 millimeters per inch. And max wells is 30. That's some kind of an economic condition. This is some kind of a economic, obviously, but some kind of drilling constraint. I don't know, something. Let's say it's drilling constraint, the economic constraint. So what is the minimum gas in place required to develop this field under these two constraints? Okay. They can't drill a bigger hole than that to put in 7-inch tubing. That's it. Okay, for whatever reason. 30 wells maximum. So then you need to come up with what is the minimum gas in place required. Okay? So you do that until 12:30.
Could you please scroll up a bit to the formula?
Which formula?
That one is okay.
Okay, this is not a, yeah. This you can ignore. You don't need to add this part here. This is a second order effect. Just ignore this. I'll take it out of my spreadsheet. It's, well, I mean, I can keep it there, but it's. Okay. I don't want this confusing the exercise. So just ignore this part here and concentrate on this one here. So you've got the drillers giving you a maximum tubing size. You've got the economists giving you a maximum development project, 30 wells. And we need to find out how large does this gas field need to be. And then we can look at the geological estimate of gas in place and see if it's within their range of the plus minus